Trigonometry, Chapter 4, Graphs of the Circular Functions, Section 4, Graphs of the Secant and Cosecant Functions, Video 1, Constructing the Graphs of the Secant and Cosecant Functions. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In previous videos, we constructed the graphs of the sine and cosine functions and pointed out key aspects of each. Both have a period of 2 pi and quarter period of pi over 2. Both have a midline of y equals 0 and amplitude 1. And starting at x equals 0, the quarter period behaviors are, for sine, middle, high, middle, low, middle, middle, high, middle, low, middle, and for cosine, high, middle, low, middle, high. Here's one cycle each of f of x equals sine of x and f of x equals cosine of x. Sine of x in red, cosine of x in blue. In this video, we construct the graphs of cosecant and secant. We achieve this by using the graphs of sine and cosine and taking the advantage of reciprocal identities. Before we start, it should be transparent that the periods of both cosecant and secant are 2 pi, since they are just reciprocals of sine and cosine, both of whom have periods of 2 pi. Let's start with cosecant. Recall that cosecant and sine are reciprocals in the sense that for any x in the domains of both, cosecant of x equals 1 over sine of x. Let's study the graphs of f of x equals sine of x to see what happens when we reciprocate the outputs. Let's start with the quarter period points. For each of these, either sine of x equals -1, sine of x equals 0, or sine of x is equal to 1. Since the reciprocal of -1 is 1 and the reciprocal of 1 is 1, the values of cosecant remain the same at these high and low points. The points highlighted in blue will be part of the graph of cosecant. But what about the quarter period points on the midline? The y-coordinates are 0 and the reciprocal of 0 is undefined. What becomes of them? Well, if you saw the video about tangent and cotangent, you already know how this goes. In order to answer that, let's see what happens as the graph of sine approaches such a point and think about what happens in terms of cosecant. So we're going to get a little analytical here. Here's a closer look at x equals pi, where the sine graph crosses the midline. As we approach x equals pi from the left of it, the graph of sine is decreasing, meaning the y values get smaller. As the value of sine gets smaller in red, the value of cosecant gets larger since they're reciprocals. How large will the value of cosecant get? That's like asking how large can the fraction 1 over n get as n approaches 0? Without getting into the calculus, the value of 1 over n will increase without bound as n gets closer to 0, if n is positive, which it is in this picture. We are above the x-axis. This means as sine of x gets closer to 0 but is positive, then cosecant of x will grow without bound and be positive. This is like saying cosecant will approach infinity. To represent this, we use a vertical asymptote at the value where sine of x equals 0. In this case, x equals pi. If you saw the tangent-cotangent video, you saw this coming. Thus, as x approaches pi from the left, the graph of f of x equals cosecant of x will approach infinity and go up forever. Using a similar argument at x equals 0, where sine of x also equals 0, we get a vertical asymptote at x equals 0, and as x approaches 0 from the right, the graph of cosecant approaches infinity. So same thing except over there. There's a vertical asymptote for the graph of cosecant anywhere the graph of sine of x hits the midline. In other words, when sine of x is equal to 0. Not the first time we've seen this phenomenon where the reciprocal of an x-intercept creates a vertical asymptote. The portion of the graph of sine between x equals pi and x equals 2 pi, so over here, does the same thing as the portion between x equals 0 and x equals pi. But because over here it's below the x-axis, the graph of cosecant approaches negative infinity and basically gets reciprocated and goes down forever. Let's go back to the larger graph of sine and bring in the vertical asymptotes for cosecant, but also the branches of the graphs between those asymptotes. All right, the midline points on the graph become vertical asymptotes, so yellow dots become vertical asymptotes. The high and the low points in blue remain the same since the reciprocals of 1 and -1 stay the same. Between each pair of asymptotes, the graph of cosecant approaches either infinity if sign is positive or negative infinity if sign is negative. So we get these disconnected parabolic looking things. Notice the high points on the graph of sine become low points on the graph of cosecant, and vice versa. The low points on the graph of sine become high points on the graph of cosecant. The blue branches bounded by asymptotes represent the graph of f of x equals cosecant of x. Here's a cleaner version by itself without the graph of sine. And there's the graph of cosecant. Now starting at x equals 0, here's the behavior of the quarter periods. At x equals 0, there's a vertical asymptote. At x equals pi over 2, the branch is a low point at pi over 2 comma 1. Used to be a high point of sine, now it's a low point of cosecant. At x equals pi, there's another vertical asymptote. At x equals 3 pi over 2, the branch has a high point at 3 pi over 2 comma -1. Again, used to be a low point on sine, now it's a high point on that branch. And at x equals 2 pi, there's a vertical asymptote. Also, there's no amplitude since the graph extends indefinitely both up and down. Now, of course, if we were adjusting the vertical stretch, then we could keep track of the high and the low points to keep track of that multiplier. Without reconstructing everything again, the graph of secant has the same relationship to the graph of its reciprocal cosine. The graph of f of x equals secant of x in blue has the same relationship to the graph of cosine in red. Everywhere cosine is -1 or 1, secant has the same value. Everywhere cosine is 0 in its midline, secant has a vertical asymptote. In my opinion, the best way to remember the graphs of cosecant and secant is to tie them to the graphs of sine and cosine respectively. X-intercepts become asymptotes. High points on sine become low points on cosecant. Low points on sine become high points on cosecant. Basically, each branch gets reciprocated, gets flipped upside down. Not really, but visually it looks that way. Now you try. Pause the video and try the following. For the functions cosecant of x and sine of x. I'll let you read it. All right. If you haven't paused the video to try to answer them, spoiler alert, solutions in 3, 2, and 1.